Electricity, man's most versatile source of power. And now man is using a powerful new source of electric power, the atom. Although many consumers may not be aware of it, the electrical energy being fed into hundreds of thousands of homes and factories is supported by atomic power. As of mid-1961, approximately 500,000 homes were receiving power produced by nuclear reactors. 1 million more homes will be using such power by 1964. But the same atoms that send power surging from huge atomic power stations, that drive atomic submarines, and power nuclear ships, are also opening new realms which only the endurance of nuclear power can conquer. When man leaves his natural environment to probe the unknown, he and the electronic explorers which precede him cannot leave behind their thirst for electrical power. Electricity is the link between our civilization and the depths of space. The same energy which lights a city must be carried into space. Just as the atom went to sea to provide man with new dimensions for action and discovery, so nuclear energy will broaden his horizons beyond the Earth. Man can use space in many ways. For communications, satellites for worldwide commercial radio, television, and radio telephone. For weather observation, worldwide long-range predictions to aid commerce, travel, and agriculture. For research, to analyze the structure of various planets and prepare for robot and manned flights. For mapping, satellites can provide the first completely accurate map of the world. For air traffic control, to maintain safety and convenience for the world's expanding air traffic. For navigation, to aid ships and aircraft at all times, in all weather, any place in the world. For astronomy, to add to the scientific knowledge of the universe and increase our present cosmological observations. For exploration, a dramatic and profound opportunity for man to extend his activities into the vast areas of the unknown. In the first 3 years of the space program, 8 successful satellites. 2 were solar probes and 36 were Earth satellites. As a result of this major space effort, man has increased his knowledge of the universe. The Van Allen radiation belt was discovered. The Earth was found to be pear-shaped. The equator was observed to be elliptical, and new facts on global weather patterns were uncovered. Power for these early experimental satellites was furnished by batteries and energy from the sun. But as space technology advanced to the more sophisticated operational satellite systems, more constant and compact power was needed. The ability of the satellites to accomplish new tasks depended upon the reliability and effectiveness of their power supplies. To meet the requirements of such reliable compact power, the United States Atomic Energy Commission in 1955 initiated SNAP, Systems for Nuclear Auxiliary Power, a research and development program to provide compact nuclear power for space and other applications on land and sea. The SNAP program uses two basic sources of heat to produce electricity. One is the energy of nuclear fission. The other is the energy of decay of radioactive isotopes. Both are a result of changes occurring in the nucleus of an atom. Building blocks of atoms are protons, which have a positive electrical charge, neutrons, which have no electrical charge but add weight to the atom, and electrons, which have a negative electrical charge. The atom is electrically neutral. The nuclear fission system uses an atomic source of heat that can be converted to electricity. This originates when the nucleus of the atom is split by a neutron. The resulting halves of the nucleus are highly energetic, and when they slow down in the surrounding material, tremendous heat is released. This heat is then converted to electricity. This splitting process is regulated and controlled in a nuclear reactor to produce a sustained nuclear reaction. The other basic system of the SNAP program utilizes the atomic source of heat from the decay of radioactive isotopes. Isotopes of a particular chemical element all have the same number of protons, but differ by the number of neutrons in their nuclei. Some isotopes are radioactive, which means that their atoms disintegrate one by one, releasing energetic particles. When these particles are stopped in the surrounding containment, heat is created. When large quantities of radioactive isotopes are contained in a nuclear generator, the heat can be converted to electricity. These two SNAP systems, nuclear reactors that control atomic fission and nuclear generators that use radioactive isotopes, are complementary to one another. Just as we need different-sized power sources to do different jobs on Earth, so we use different types of atomic power systems to carry out various tasks in space. Selection of one or the other depends on the needs of a particular mission. Many factors govern the use of SNAP units, such as the mission, weight restrictions, frequency of radio transmissions, and peak power requirements. A historic milestone was reached in January of 1959, when former President Eisenhower announced the successful operation of the first SNAP power unit. This isotopic power unit is called SNAP-3. In this device, the spontaneous decay of a radioisotope generates heat in the surrounding container, which is converted directly into electrical power by a series of thermocouples made of a semiconductor material. There are no moving parts. Potential lifetime of the unit is limited only by the radioactive half-life of the atomic fuel. In June of 1961, another member of the SNAP family, developed by Martin Marietta Corporation, was successfully launched on board the Transit satellite, the world's first use of nuclear power in space. This SNAP device was installed on the Navy's Transit 4A navigation satellite. It produces almost 3 electrical watts, enough to power 2 of the satellite's 4 radio transmitter systems for 5 years or more. It gets this energy from fuel sealed in a capsule material. The capsule contains the radioactive isotope plutonium-238. The capsule containing the isotope is welded closed. The isotope cannot escape from its container, even if the launching rocket should explode or if the capsule should fall into the ocean. Once the fuel capsule is inserted in the generator, radiation from the unit is at a level safe for prolonged exposure of personnel. The fuel capsule is placed in a thermoelectric generator that converts the decay heat of the isotope directly to electrical power. The generator weighs about 4 1/2 pounds. It is about 4 3/4 inches in diameter and 5 inches high. There is not a single moving part in the entire system. The exterior is flame sprayed with a white ceramic coating that helps dissipate internal heat and rejects most of the solar energy that will strike it when the unit is in orbit. The current from the generator passes through a converter that steps up the voltage to the various levels needed for the radio transmitters and other instrumentation. Electronic components of the converter have been embedded in a plastic compound so that they withstand the shock and vibration of rocket launching and flight. At the Applied Physics Laboratory of the Johns Hopkins University, prime contractor for transit, the satellite and its snap power sources were subjected to flight acceptance tests to assure complete systems integrity before launching. Transit 4A was installed with its radioisotope fuel generator on the Thor Able Star booster. On the evening of June 28, 1961, final stages of the countdown began. By 20 minutes after 11, Cape time, Transit 4A was at T-3 minutes and counting. Transit was injected into a 575-mile orbit. Its isotopic-powered navigation equipment is transmitting precise signals which are being received all over the world, indicating that the generator is operating properly in its space environment. The operational transit satellite system will provide navigational information from which aircraft and ships around the world will be able to fix their positions within 1/10 of a mile. A new navigator's friend is taking up position with long familiar stars to guide man across sea, land, and sky. Success of transit marked a major step in development of peaceful uses for nuclear energy, the first application of atomic power in space. Another outstanding example of snap power units for space are the nuclear reactors being developed by Atomics International, a division of North American Aviation. This compact nuclear reactor, SNAP-2, coupled to a small turbo generator, will provide 3,000 watts of electricity in space for 1 year. The entire system weighs about 1,000 pounds. In this SNAP reactor, the nuclear chain reaction is controlled by movable reflectors. A coolant is used in the reactor to remove the heat. This maintains a constant temperature in the reactor. Heat from the reactor is carried by the flow of coolant to a boiler, which transfers the heat to mercury. Mercury is converted into vapor, which expands in the turbine and provides the power for operation. The turbine, which is connected to an alternator, generates a continuous supply of electricity. The system works on the same principle as ordinary steam electric generators, except that mercury vapor instead of steam drives the turbines. A reactor system similar to this, called SNAP-8, is being developed for the Atomic Energy Commission and the National Aeronautics and Space Administration. The SNAP-8 system will generate up to 60,000 watts of electricity and will pioneer electric propulsion in the United States space program after 1965. Another system, designated SNAP 10A, will be the first reactor power system to be flight tested. In this system, heat energy is directly converted to electric energy by a thermocouple system. There are no mechanical moving parts during operation. This system will start up after it is in a stable orbit and will produce 500 watts of electrical power continuously for 1 year. Much effort has been expended to minimize hazards and ensure safety in handling and inspection of all SNAP units. Since the fuel of the isotope devices is radioactive in itself, the fuel capsule has been designed to keep it sealed on the pad during launch and in orbit. Extensive tests were conducted to check the integrity of the fuel capsules. For example, heated isotope containers were impacted against cold water and against one of the hardest known surfaces on Earth, granite, at 340 miles per hour. They were deformed by impact on granite, but they did not release the simulated fuel. Nuclear capsules were put in a test tower, calculated to equal the burning rate and temperature of a burning launch vehicle. Although the nuclear capsules were scorched, they were intact and not burned. Capsules were placed in 1,650 pounds of TNT to simulate the explosion of a launch vehicle on a launch pad. All recovered capsules were undamaged, and none of the simulated fuel was released. When a generator is ready to re-enter the atmosphere, safety requirements change. Instead of containment, it is now safer to let the generator vaporize and disperse. Plasma jet tests have confirmed that the generator and capsule will burn up totally during re-entry. The fuel will disperse safely in the atmosphere, resulting in a radiation level too small to be measured by existing instruments. Safety has also been a primary concern in the development of nuclear reactor systems for space use. The reactor cannot operate without its reflectors completely enclosing the core. Since the nuclear reactor systems are not radioactive until they are put into operation, personnel can handle fuel elements and install systems before launch with safety and ease. To ensure complete safety, reflectors can be shipped separately to the launch site. Reflectors will be installed at the site in an unfolded position. This simplicity of design and operation ensures that the reactor will not be operating, will not be producing any radioactivity until it is in orbit in outer space. In addition, reactor systems will withstand the severe shocks, vibrations, and temperature changes associated with a launching vehicle, and will not constitute a hazard to personnel, facilities, or the general public. After orbit lifetime is completed, all radioactive material would either decay or be dispersed in the atmosphere. This simulation shows a reactor satellite at an altitude of approximately 80 miles. Heating of the vehicle is slight, but the heating increases until the entire reactor disintegrates into small pieces at an altitude of over 100,000 feet, 20 miles above the Earth. Because of their characteristics, SNAP units have been adapted for special uses on Earth. They have applications on ground as well as in space. Under the Commission's programs for development of power systems, an unmanned generator is now in operation in the Canadian Arctic, transmitting weather data to permanent Canadian and U.S. stations. A more powerful version of this unit, with a potential life of 10 years, SNAP 7C, will supply power for an unmanned automatic weather station in the Antarctic. This unit will broadcast temperature, wind velocity, wind direction, and barometric pressure from an outpost near the Little America station. Other SNAP 7 devices will be employed for sea buoys and land-based lights to aid the Navy and the Coast Guard as navigation beacons. The more powerful SNAP reactor plants also have a use as portable electric power sources. These portable reactor power plants could be mounted on barges for industrial needs, transported by air for power generation in remote areas, or carried by vehicles and used as mobile power plants. It is becoming increasingly apparent that the progress and growth of our civilization will accelerate with the development of atomic power. SNAP units will affect life on this Earth, but also will have a significant role in man's exploration of space, and finally, the utilization of space. All forms of telecommunication, such as the telephone, telegraphy, and teletype, will be greatly extended and improved. For communications, we may soon see satellites hovering in equatorial orbit above the Earth. These stations will relay news, entertainment, and special events that can be seen and heard around the world. Programs can be relayed from space without static. Two-way telephone television will become a reality.
We shall propose, finally, a global systems of communication satellites linking the whole world in telegraph and telephone and radio and television. The day need not be far away when such a system will televise the proceedings of this body to every corner of the world for the benefit of peace.
Several languages could be simultaneously broadcast with a single picture. Weather observation satellites will provide data for worldwide long-range weather predictions for the betterment of world agriculture, travel, commerce, and daily living. Long-range weather surveillance of this kind will be of great value to the world in preventing storm damage and assisting crop growers. Air traffic control, mapping, and navigation will be vastly improved by SNAP-powered satellites. Many important events are scheduled, including several flights to send American astronauts around the Earth. In the coming decade, over 200 satellites and spaceships are predicted to be launched by the United States. Packages containing television, radio, and recording instruments will make hard landings on the moon. The Surveyor craft is scheduled to make soft landings on the moon. With larger launch vehicles, the United States plans to place mobile laboratories on the moon. These laboratories will dig up samples of lunar surface and return them to the Earth. Other spacecraft will land on the moon, explore a large area of its surface, and transmit photographs back to Earth. Space vehicles will fly past Mars, Venus, and other planets, photographing and sending back information. Voyager spacecraft will land instruments on Venus and Mars. These instruments will radio information to a mother spacecraft, which will relay messages to the Earth. These robot space probes will greatly add to man's knowledge of the universe. Later, an Apollo spaceship is due to take 3 astronauts into orbit around the Earth. Then the astronauts will be launched on a trip around the moon, and finally sent to land on the moon, and then return to Earth. As space vehicles penetrate deeper into outer space, more and more electric power will be required over extended periods for guidance, attitude control, telemetric devices, communications, and the support of human activity. Man has always been a most versatile being. He has used his intelligence and skill to probe the secrets of the universe. Who knows what future missions will be planned? What space vehicle will be used? Perhaps a nuclear electric-propelled manned spacecraft spiraling out from the Earth on its way to Mars and beyond. Atoms for space.